Well, thank you very much. I want to thank the Royal Swedish Academy of Sciences, the Nobel Foundation for recognizing our work. I want to particularly thank my colleagues and teammates on the High-Z team and the Higher-Z team for sharing this science adventure. Brian called it a science fairy tale. I see it as an adventure story. We'll see what you think at the end. I'm going to continue telling the story of how observations of exploding stars revealed that we live in this very strange universe, not only expanding, but accelerating. And now I'll answer Brian what we did wrong. I got interested in this subject of measuring the universe when I came to understand that one could answer really big questions. How old is the universe? How big is the universe? What is the ultimate fate of the universe? By measuring the rate at which the universe expands. And if you measured that very precisely and also measured it, as Brian described, back into the past to see how the expansion rate changes with time, you actually could answer these questions that seem just like philosophers' questions, were actually something that you could answer with careful measurements of redshifts and distances, as Brian described. So when I started graduate school in the early 1990s, the expectation was that we lived in a universe that resembled either the one on the left or the one on the right. Either we lived in a very heavyweight universe, a very massive, dense universe, whose mutual gravity, the attraction of all the material in the universe, would rapidly slow down this expansion that came after the Big Bang, so that eventually the expansion would stop, the universe would start to recollapse, and we would have the opposite of the Big Bang. Brian called it a funny name, but I'll call it the Big Crunch. Or we lived in a very lightweight universe that had such little material in it that it was only modestly decelerating, in which case we would say the universe had escape velocity from itself. Like if you launched a rocket with enough speed, it would get away. And so we could have lived in either of these, or we could have lived in the knife edge case, exactly the right mass that the universe would stop expanding, but only when it reached infinite size. And by the early 1990s, it became clear that our best method for determining which universe we lived in would be to find these exploding stars, especially the ones in the past, that could give us the history of the expansion rate of the universe throughout time. And by measuring the deceleration, by seeing if it was very large or very small, we would, in essence, weigh the universe to determine its ultimate fate. By the early 1990s, by the time I started graduate school, it was thought that these type 1a supernovae, these stars which had attained the Chandrasekhar limit and exploded, would make great standard candles, although as Brian described, it also became clear that perhaps they were not going to be perfect. The idea behind a standard candle is just a simple rule. If it's bright, it's nearby. If it's faint, it's far. That works very well if they really are all the same. But 1991 really was a watershed year for understanding type 1a supernovae. Nature gave us the bookends of the class, the most luminous one we had ever seen and the least luminous one we had ever seen. And it was kind of hard to ignore that they were not really all the same, that we would have to come up with a way to account for these differences, much in the way that Mark Phillips described in his seminal 1993 paper, that the ones that are intrinsically dimmer will fall faster after they reach their peak. I became interested in another problem that was related to this when I started graduate school, and that is another reason that a supernova could appear faint, not just that it was far away, not just that it was intrinsically dim, but sometimes in galaxies there is dust, and the dust will screen or scatter the light of the supernova, making it look faint and fooling you into thinking it's further away. Now, the kind of dust we're familiar with is more efficient at scattering blue light than red light, which means more red light comes through, and so it also not just dims, but reddens the light. And so there was a hope that you could use this telltale reddening to tell that when a supernova looked faint and red, then it really was not so far away. And so a lot of the foundations of this work was laid by the Keelan-Tololo survey in the early 90s, which collected some of the early foundational data on supernovae to help us begin to think about these concepts. Now, when I started in graduate school, these are my academic parents. We were a very progressive family. Massachusetts was a very liberal state. And so I worked with Bill Press and Bob Kirshner. And we developed a different formalism, a different way of measuring the supernova light curves called the multicolor light curve shape method. The idea was to combine both of these effects. The fact that the supernovae were not all the same intrinsic brightness and that sometimes they had dust in front of them. So that is, we wanted to distinguish when faint meant far away, when faint meant intrinsically dim, so not so far away, or when faint meant dusty, and again, not so far away. And we developed a fairly strong statistical machinery to make these simultaneous corrections, to use measurements of the supernova throughout its whole history to deal with the relation between different kinds of errors in the data, and to make use of simulations from galaxies to give us extra information about how much of this dust was in the galaxies we were looking at. By 1998, we had added an extra feature even to be able to make use of missing epochs of data, all in the interest of trying to improve our ability to measure the expansion rate of the universe. And this was a key figure from my thesis. This is one of these diagrams intending to measure the rate at which the universe expands from determining where the line is that goes through the data, but you can see a number of objects which have scattered very far away, in particular in the direction where it looks like the supernovae are faint, and so you think they're far away, but they're really faint for different reasons that don't have much to do with distance. In some cases, dusty, in some cases, intrinsically dim. And so when we applied this machinery, we found that with many less supernovae, we would be able to make a very powerful measure of the expansion of the universe. The other part of my thesis at Harvard with Bob Kirshner was to collect the first large sample of supernova light curves in the north. The Keelan-Tololo survey was in the south. And by the end of 3 or 4 years of hard work with the 1.2 meter on Mount Hopkins with the CFA crew, we'd collected 1,200 observations of 22 of these type 1a supernovae in 4 colors. These are the light curves. This is just the light history of the supernova as it rises and then declines. And so we were able to, with this set, make a very precise measurement of the expansion rate of the universe nearby at the present time, telling us how fast the universe was expanding. So as Brian described, by early 1994, a number of us that would form this team had been working hard to measure nearby supernovae, learning everything we could about how to measure their distances. And at some point, we started to become confident that we could take this knowledge and go after the sort of big game at high redshift, the kind of objects that would give us this past information about the universe. And so we set out to, and I emphasize this here, every team needs a credo, and our credo was to measure the cosmic deceleration rate because that's what we thought would be going on. And these are the best pictures I could find. It seemed that we tended to gather in Aspen, Colorado. In Aspen, Colorado, these clothes are what resembles the tuxedo and tails that you wear in Stockholm. And so by 1996, I had gone to Berkeley to work with Alex Filippenko, and we went on observing runs at the Keck Observatory, as Brian showed in his movie, trying to confirm the type of supernovae that the crew in Chile found by sifting through these images. I was also at the time improving these algorithms and also had begun to analyze these pixelated images of supernovae that our team had collected. And I just want to emphasize how challenging this was. Here on the left is the kind of supernova that we had been working with nearby, that we had sort of cut our teeth on. And in fact, my thesis advisor cut his teeth on this one in particular, 1972E. This is a supernova 10 million light years away. And so here's the usual shot before and after. And so the goal is to measure how bright that supernova is to figure out how far away it was. By the mid-90s, the goal had become 1,000 times harder, well, really 1,000,000 times harder, because the supernovae were 1,000 times further away than the ones we were trying to measure by 1996, which means they were 1,000,000 times fainter. There's not often in science you learn how to do something and then try to do it when the level of difficulty has been raised by a factor of 1,000,000. And so this whole galaxy now has shrunk more or less to live in just a couple of pixels. And when the supernova goes off, you can no longer separate the light of that from the galaxy. These couple of pixels have gotten brighter, and you need to tease out that little bit of excess light in order to measure the distance to the supernova. So this was hard work. By 1997, and by the fall in particular, I had been picked by our team to analyze our first really large sample of supernovae, about 16. And having done all the steps in the analysis came the moment of truth where the deceleration rate, which we write in the variable Q naught, set by the supernovae, would then imply how much mass was in the universe. If it was decelerating a lot, if this was a big number, then the mass of the universe would be a big number and the universe would recollapse. So I wrote a simple computer program to tell me what the answer was, and hadn't yet noticed that something very strange was going on. So this is a key page from my lab notebook. When I evaluated what the mass of the universe was, I got an unphysical, nonsensical answer, a negative value. That wasn't even one of the possibilities. It wasn't in column A or column B. It was very strange, and what it meant was if this term was negative, that really meant this term on the left was negative. That is, the universe wasn't decelerating, it was accelerating. And I just hadn't noticed it. And when you ask a computer sort of a dumb question, you get a dumb answer, which is the universe would have to have negative mass. Now, the real reason is because I assumed this thing that Brian had described, this cosmological constant, didn't exist. And so I quickly realized that the other way to get this number on the left to be negative, for the universe to accelerate, is to have an overwhelming amount of this term on the right, this Einstein's cosmological constant. And so a few days later, I began considering whether that indeed was required by our data. And another calculation showed, yes, at what we would call good confidence in the statistics, this wasn't a fluke. At 99.7% confidence, this is what our data was showing. So this was extremely surprising. I assumed, Brian said, what did I do wrong? That was exactly my thought. What did I do wrong? I can't believe we didn't even get close to the right answer. And so I went through a series of checks, but I couldn't find what I had done wrong, and then began to talk to the team about what we as a group had done wrong. And this was a very fun time and exciting, and the best way I can bring my colleagues who are out in the audience back onto the stage with me is to share with you a couple of days of very excited, very tense discussion back and forth over email. And so that's what I'm going to do now. So this was, you can imagine, just upon seeing these results more widely in the team, Alex Filipenko started out the dialogue. Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. I should say I got married just a couple days before this, so it was a very exciting time. Bruno Leibengut from Germany wrote, concerning a cosmological constant, I'd like to ask Adam or anyone else in the group if they feel prepared enough to defend the answer. There is no point in writing an article if we are not very sure we are getting the right answer. Brian Schmidt, I agree our data imply a cosmological constant, but how confident are we in this result? I find it very perplexing. Bob Kirshner, I am worried. In your heart, you know the cosmological constant is wrong, though your head tells you that you don't care, and you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant, only to retract it next year. Mark Phillips from Chile wrote, as serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. John Tonry from Hawaii reminds us, Who remembers the detection of the magnetic monopole and other gaffes? On the other hand, we should not be shy about getting our results out. Alex Filipenko again, if we are wrong in the end, then so be it. At least we ran in the race. I came back from my wedding, repacked to go to my honeymoon, and typed out a quick email. The results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I have. And I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers after all. And Alejandra wrote, very amusing, if Einstein made a mistake with the cosmological constant, why couldn't we? I could never tell whether this was a vote of confidence or a statement that if you're wrong, you need good company. And then Nick Sunsef wrote, I really encourage you, Adam, to work your butt off on this. We need to be careful. If you are really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have another scientific result that is more exciting come your way in your lifetime. And of course, Nick was, as usual, right. So after about another 6 or 8 weeks of trying everything we could to knock the result down, we felt we couldn't and that we had to come out with the face value interpretation. And we published this paper, Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant, implying that the universe was accelerating at a degree that about 70% of the energy of the universe would be in the form of this cosmological constant, or more generally, dark energy. And with the other team reaching the same conclusion, Saul will talk about that, this became the breakthrough of the year for 1998. But just because it was the breakthrough of the year, we didn't stop working. We were very concerned that there still could be something wrong, something subtle. This is the data from the two teams overplotted. These are the nearby supernovae that we've described, and these are the distant ones from the two teams. And as Brian described, the important signal was that the distant ones, the ones coming from the past, were fainter than you would have expected without the universe accelerating. And this was all based on the interpretation that faint equals far, that after we made these corrections, after we accounted for everything we could, that the fact that these supernovae were extra faint meant they were extra far and the universe was accelerating. So we thought hard about what else could mimic this, and others thought hard too. And in particular, Anthony Aguirre, a theorist at Santa Cruz, wrote a series of bracing papers arguing that as weird as the cosmological constant was, what if there was something else weird in the universe? He called it gray dust. This would be a special kind of dust that did not change the color of a supernova, that did not live in the galaxies of the supernovae themselves, but lived between the galaxies. And by looking through this gray dust, we were losing a lot of our light and being fooled into thinking that the supernovae were really far away when they were just faint because of this gray dust. Or it could have been that the supernovae born when the universe was younger were born fainter, just intrinsically dimmer. And so a very powerful test was suggested by around 2000, which is if we could push out and look at even more distant supernovae, we would be able to tell the difference. Because if this dimming due to this mysterious gray dust or supernovae being born fainter was present, presumably it would continue. Whereas a funny thing happens in a universe filled with dark energy. Dark energy only becomes dominant when the universe becomes very large. When it's small, it's more compact. And when it's compact, objects are closer together, and the attractive form of gravity, the pull between objects, becomes more important. And just as acceleration makes objects look further and fainter, deceleration makes them look closer and brighter. So we thought if we could go out further, we would see a transition, a turnover, when the universe was decelerating before it began accelerating. To tell the difference between these, we had to find even more distant supernovae, more distant than we had been able to find in the past from the ground, which leads me to an explanation of how astronomers often rest on the power of their telescopes getting better and better. Here is the improvement in the telescope over the eye from Galileo through the time when telescopes got bigger, moved to better locations, and got better detectors, and ultimately we placed them into space with the Hubble Space Telescope above the atmosphere so that we could separate the light of a supernova from its host galaxy from the same seen from the ground. And sometimes we're lucky that astronauts go back to those telescopes and improve them with new detectors. And so in 2001, well, in 1997, HISE team members Ron Gilliland and Mark Phillips found what looked like an ultra-distant supernova they called 1997 FF, and I was lucky enough in 2001 to find many more observations of that supernova that were sitting in the archive, having been taken as part of the commissioning of a new camera. And so it was a very lucky set of observations, but even this one indicated it was way beyond anything we had ever measured and did support the accelerating interpretation of the supernovae, that we could see the universe decelerating before it was accelerating. But this was only a single object, and as Brian said earlier, scientists don't like to rest conclusions on a single object. But the whole story changed in 2002. The astronauts returned to Hubble, and they put a new camera in, the advanced camera, which made it relatively easy to find ultra-distant Type 1a supernovae. And I led a team that from 2002 to 2007 found about 23 of these objects, took their spectra, discovered them by subtracting images, and now looking at this kind of curve Brian had been showing and I showed earlier, the universe has only been accelerating recently relative to a coasting universe shown by the straight line. It's accelerating here, but if you go way back into the past, you see this turnover. It was decelerating, and there's no evidence of some kind of dimming that would have been throwing off our observations. So we were confident in the supernovae, but at this point, it's not just supernovae which argue that the universe is filled with a mysterious dark energy that accelerates the universe. I go over a few reasons. Supernovae were the first to show the universe was accelerating. More recently, we've seen that when we look at photons of light from the early universe, as they cross through the gravitational field of galaxies, they lose energy, they gain energy, and then they lose it as they climb back out. But a funny thing happens to those galaxy clusters. They are pried apart by dark energy as the photons make this trip, and so we see a net change in the energy of the photons. This was first detected in 2003, implying the universe is 70% dark energy as well. We have also seen in observations of the cosmic microwave background that space-time has been smashed flat by all of the energy in the universe, and yet we can only account for 30% of that in matter, which means that there's a 70% missing component, the same 70% seen here and here. And then two other effects we've seen more recently, that the largest clusters of galaxies, which pull new galaxies in, have become less and less effective at doing that because of dark energy. And finally, we've seen a change in the absolute scale of the universe, as first seen at the time of the Big Bang and now measured today. All of these lines of evidence are independent, and yet all of them tell us the universe is about 70% in the form of this funny energy. So at this point, we're pretty confident that it's there. What we're not confident is why is it there? Brian described Einstein's original idea, the cosmological constant, that you could have a constant amount of energy in space. As weird as this sounds, it's actually predicted at some level from quantum theory. In fact, it's hard to get rid of it in quantum theory. And a consequence of this in general relativity is that it will cause repulsive gravity. As long as there's a lot of it, there is a bit of a calculation problem. When we try to calculate how much there should be, we get a number that has about 120 orders of magnitude too large, but the theorists say they're working on it. It could be that we have a dynamical dark energy. This would be an energy field in space. Think of the magnetic fields or the electric field. This would be a different field, and it would be temporary, changing with time. It would work by a similar mechanism, and we have called on this before to explain the first moments after the Big Bang. And of course, it's always possible that we are on the cusp of a revolution in our understanding of gravity, that even Einstein didn't have gravity right, that we have finally seen the failures of gravity as we have gone to the largest scales, and the theorists are working on that too. The observers, however, are working on tests of all three of these by checking the strength of dark energy. Has it been constant like this? Has it been changing like this? Or does it change just when you get to different scales of the universe? So what we're excited about recently is the astronauts have returned to Hubble for the last time and have put a new camera in, and this is helping our studies of dark energy. Already we've been able to improve the precision of the measurement of the expansion rate quite substantially, and we've begun to push even further back toward the beginning of the universe to look for the very first supernovae of type 1a, which exploded. So I want to end with a sort of philosophical note. This is our universe. This is the recipe. I think this is one of the great accomplishments of 20th century cosmology, is just to give names to all these objects. It turns out it's very humbling. Only about 4% of the universe is made of the stuff we're familiar with. 25% is dark matter, which is quite mysterious, and 70% is dark energy, which is even more mysterious. These are things that we only see by their gravity. These are things we see by their light. So why is it that we're so excited about dark energy, or whatever the cause of acceleration is? Well, it's 70% of the universe, so that's a big piece of the universe that you need to understand to say we understand the universe. We've learned it will determine the fate and the origin of the universe. Until we understand dark energy, we can't really answer those questions. But I think what we're most excited about with dark energy is we have two very powerful theories in physics. We have quantum theory, which is sort of our rule book for small objects in the universe, and we have general relativity, which is sort of our rule book for large objects. And these theories don't work together, and we don't try to apply them together. But understanding dark energy requires us to understand both these theories and how they meet. We don't know, as physicists, how to do that problem, so it's very helpful to see how nature actually does it. And so that's why we keep following the dark energy. So I will end there with a summary, and thank you very much for your time.